Here we are in same house as parent v3, and what I asked you to do was to start the design of the same house as parent function and take it all the way up through the template stage. So of course, if you had to do it, I had to do it. So it's going to consume a wizard and produce a list of string, and it produces the names of every descendant in the same house as their parent. And I put 4 examples. I put A, because that's the simplest case. A wizard with no descendants has to produce empty. I put H, because that's a relatively simple case. It's a wizard whose only descendant isn't in the same house. That produces empty. And I put G, because that's another relatively simple case. A wizard with a single descendant that's in the same house, we produce the name of that descendant. And then I put K, because it's a nice big example. And then I templated from wizard. In other words, I took this template up here, and I added an accumulator to serve as a lost context accumulator. Now notice in this template that I added the accumulator to both functions. When you've got mutually recursive functions and you add an accumulator, you need to add the accumulator to all the functions. So parent house got added as a parameter to fun for wiz, and it got added as a parameter to fun for LOW. I put it in both functions and in all the mutually recursive calls. Okay. That's really important. When you add an accumulator to mutually recursive functions, it's got to go in all the functions. And what I'm doing here, since that ends up being a relatively complicated template, is I've left that description, template from wizard plus the lost context accumulator. Now, why did I know it was going to be a lost context accumulator? Well, let's go back and look at our picture. If we think about what's going to happen, we're going to go through this tree according to the structural recursion template. So we'll start at K, and then we'll go to H, and then we'll go to C, and then D, and we'll go through the tree that way. But at each point in that traversal, we're going to need to know, gee, is this wizard in the same house as its parent? Because if it is, we want to include it in the list, and if it's not, we don't. That's a classic example of the thing that the structural recursion template will lose. The structural recursion template will give us this wizard, and it'll give us this wizard's name and this wizard's house, but it won't tell us about the parent, because that's the prior recursive call. So I know I need a lost context accumulator, and in this case, I know what I need the lost context accumulator to be. By the time I get to H, I want the lost context accumulator to be the parent's house. In other words, G. By the time I get to C, I want the lost context accumulator to be the parent's house. In other words, S. At D, I also want it to be S, and so on. So instead of calling the accumulator ACC, I went ahead and called the accumulator parent house. I could have called it ACC, but I know it's going to be the parent house, and so I called it parent house. So now what I have to do is finish the design of this function, starting with the accumulator type, the example progression through a tree, and of course filling in the code. I'm not going to stop and switch to a next video here because I'm actually going to work through this, but you might want to pause the video at least and work on it yourself. Okay, I hope you solved it before continuing the video, but if not, still have time to go back and do it. Anyways, so let's see. We know what the parent house is. It's the house of the parent. And we know from the type definition for wizard that a house is a string. So, you know, the type of parent house has got to be string. And what is it? It's the house of this wizard's immediate parent. Now there's a little ambiguity that comes up here. Maybe you see it now, maybe you don't. Let's keep going and we'll have it come up. Let's suppose that we call same house as parent, and now this is the top level same house as parent, and we call it with WK. So now the immediate thing that happens is the trampoline calls fun for wiz with WK and some value for the accumulator. And oops, let's see. How do I get this to work? I'll kill there. And so there's going to be a progression. So we go from K to H to C, and then briefly back up to H to D, and then to I, and so on. So this is the first call to the inner function. This is the trampoline call. So when this calls K, what's the house of the parent? We don't know. We don't know the house of the parent. The parent doesn't have a house. There isn't a parent. How could it have a house? But, we got to put something here. And since we know that houses are strings, and in fact we know that they're always S, G, R, or H, I'm just going to decide to put the empty string here as a way of saying we don't know what this parent's house is. And I might take the trouble to put a little note here that says for root of tree. Just as a way of remembering that I decided that I was going to use the special value empty string for the root of the tree. So when we make the first call for WK, it's the empty string. And let's see, when we get to H, it should be G. And that means that when we call fun for whiz with WH, the second argument has to be G. Now notice that I'm leaving out the fun for LOW in the progression of examples. Sometimes when you do a progression of examples for mutually recursive functions, you'll want to include that. Sometimes you might not need it. I'm starting assuming that it'll just be enough to just mark it for the wizard functions and not the LOW calls. Might turn out to be wrong, we'll see. So let's see, so when we call it with H, the parent house should be G. When we call it for WC, the parent house should be S. And when we call it with WD, the parent house should also be S. And when we call it for WI, the parent house should be G, and so on. If you didn't pause before, here would be a really good place to pause and finish it up yourself. But let's finish it up. This is kind of like a filter function, right? We're going to traverse this whole tree and we're going to produce a list of just some of the wizard names. So how do we know that a given wizard is one that we want to include or not? Well, right here, fun for whiz is the function that operates on wizards. And the question really is going to be, I'm going to grab this right here, and I'm going to say, hey, if this wizard's house, I'll put it in this order even so it reads a little bit better, if this wizard's house is the same as the parent's house, there's the question, is this wizard's house the same as the parent's house? If that's true, then what do I do? Well, then I'm going to put this wizard's name into the natural recursion. And if this wizard's house is not the same as the parent's house, then I'm not going to put this wizard's name into the natural recursion. Whoops. So I'll just have the natural recursion. I'm ignoring this accumulator argument to the functions for just a second. I'm trying to do kind of the filtering stuff first. So that's the filtering stuff. So when you filter, the base case of the recursion is empty. And what happens here? Well, this is kind of filter operating on a tree. Fun for whiz produces a list. Fun for LOW doesn't really care about the parent house. Fun for LOW just needs to take whatever fun for whiz produces, which is a list of wizard names, and whatever it's going to produce, which probably better be a list of wizard names, and combine those together. So to combine two lists together, that's an append. So now I've sort of got the filtering behavior added to the template. Now let's think about taking care of the accumulator parameters. Well, let's see. At the very beginning, we've already said right here that when the trampoline calls into the mutual recursion, it's going to provide the empty string. What happens here? What happens here? Well, let's see. This function fun for Wiz is at a wizard, and it calls fun for LOW to operate on the wizard's children. The invariant says that parent house has to be the house of this wizard's immediate parent. So when a given wizard goes to operate on its children, the accumulator has to become this current wizard's house. So what we're going to do here is completely replace the existing accumulator value with the house of this wizard. And both natural recursions have to do the same thing. Right? That preserves the accumulator invariant. When a wizard goes to operate on its children, it does it with parent house being that wizard's house. Here we're going through a list of children. What happens to the parent house as we go through the list of children? Well, nothing. It doesn't change. Right? All of the children have the same parent. So what we'll do here is we'll just preserve whatever value of parent house we were given, and we'll do the same for both kinds of recursion, the natural recursion and the natural mutual recursion. Let's try that. All 4 tests pass. So reviewing it quickly, look, it starts out as an ordinary HCDF problem. Boom, 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 boom. Then I templated from wizard, and I realized I needed a lost context accumulator. Then I did all my accumulator type, invariant, and examples. And I filled it in kind of 2 steps. I realized it was a filter problem, so I filled in the filter aspects of it. And then I filled in preserving the accumulator invariant as we went along. Quite a lot going on there. What I want to ask you to do now is really be sure you're comfortable with that before proceeding. So, you might want to replay that or do it yourself or something else before proceeding. In a sense, it's just review of what's come so far this module, except that now we're doing it to an arbitrary arity tree, or I should say, except now the recursion is through an arbitrary arity tree instead of through a list. But this is, quote, just a lost context accumulator being carried along through an arbitrary arity tree. I say just, but it's not that simple. So please take the time to be sure you're comfortable with it before playing the next video.